Okay, Stat Nation, this is chapter 5, day 4. Let me share my screen. Probability is, like I've said in previous videos, is the single most requested information of all. People always want me to repeat these, so I've taped a few of these. Now, the structure of the way I did this chapter is I think probability can be so complex for kids or anybody that literally the first 5 days of chapter 5 are literally warm up. So I don't get into specific skills that will be tested until like day 6. So keep that in mind. So like I always say in these videos, feel free to stop, go back, repeat. It's going to take some time. But I keep introducing concepts, so when we finally get them, we'll be good to go, okay? So let's look at what we're trying to do today, standards and objectives wise. We're trying to learn that the intersection, the and of problems, multiplication will work if the two events are deemed independent. Sometimes you're told they're independent. Sometimes you have to discover if they're independent, and we're going to do that to both of those today. Now, this is a pretty important formula for OR. Remember, OR has the union symbol, which is the U, so to speak, there, while intersection has this symbol right here, okay? And the formula is probability of A plus B minus their intersection. And we talked about this in the previous video. This intersection can be one of 3 things. It can be 0 if the events are deemed to be mutually exclusive or disjoint, meaning they cannot happen at the same time. That intersection could be the product of A times B if the events are independent. And it could be some given number or given percentage if the events are not mutually exclusive nor independent, okay? And again, in subsequent days, you're going to see this. But in the first 5 days of chapter 5, I just do all kinds of crazy probability problems. Some you can handle, some you can't, just to see where kids are at and everybody's at, okay? All right, let's go through some of these and see if they are independent or dependent. You can obviously see my answer key. So 1A, rolling a pair of dice and getting an even sum, then getting an odd. So 2 different rolls. You probably realize that every roll of a dice is independent. The next roll has nothing to do with the previous roll. That's independent. For 1B, randomly selecting one student from this class to move to period 0, then selecting one to move to 7. Well, you can't select the same student twice. So when you select one student, that changes the probability of the next student being selected. So that is a dependent situation. The NFL draft, of course, is a major dependent situation where if I take a quarterback with pick 1, you clearly can't take that same player. So that, again, is a dependent situation. Now, mathematically, let's go down to 1D. We're going to see if these are dependent or independent, okay? All right, so what we have here is probability of A is 2/5, B is 1/4, and the intersection is given to us as 2/15. All right, to see if they are independent, I'm just going to multiply 2/5 times 1/4, and that equals, canceling here, that equals 1/10. But we're told it's actually 2/15. So there is some dependence here. These are considered dependent, okay? So there is one of the 3 ways things can intersect for you. Remember, if it's 0, the intersection, it's mutually exclusive. If it's the product of A and B, they are considered independent. And if it's given like this, it's neither mutually exclusive nor independent. Okay, it's a given one. Great. Okay, how about this one? We're going to multiply 0.27 times, I guess, 0.2. And that does not equal this. It does not. Again, these are dependent situations. Okay. Now here's one that's independent. If you multiply 0.82 times 0.15, you will get this. Okay. So when the intersection is their product, they are definitely independent situations and have no effect on each other and just show up together when kind of randomly. There's no dependence on that. Okay. All right. So again, independence has to do with multiplication. Mutually exclusivity has to do with the summation of things. So let me move the screen up a little bit. Okay. Let's go right to here now. Okay, so are these events mutually exclusive or not? Disjoint or not? And again, mutually exclusive means can't happen at the same time. Okay. All right. When you flip a coin and it lands on heads or lands on tails, a coin cannot land on both heads and tails. Don't say sideways. It can't land on both heads and tails. So those two events are definitely mutually exclusive. Now, for the citizenship of a person, can you be a U.S. citizen and a Canadian citizen? Yes, you can. You can be both. Now, this is weird now. We're gonna say not mutually exclusive. That's a double negative. So not mutually exclusive means it can happen at the same time because you can be a citizen of two countries. And then the next one, a six-sided die is rolled once, a 3 or higher or an even number. Well, a 3 or higher is a 4, a 5, and a 6, and an even number is still is there. So those can happen at the same time. So those are called not mutually exclusive, meaning they can happen at the same time. It's a double negative. Okay, part 2. Okay, part 2. This is a review. I have put this up in other days of our lessons, okay? So let's review a few things. A probability is between 0 and 1. 0 means never, like the chances of Mr. Snyder getting a date when he was a kid, 0. And 1 is all the time. The chances of Mr. Snyder making a free throw, 100%. Don't I wish? All right. Now this right here means the sum, that's the summation symbol, of every individual event times its probability is 1. If you add all the events up in a set, it'll equal 1. You can't get over 100%. Okay. And of course, you know the complement. The complement is 1 minus the probability that it will occur. That is actually heavily used in certain types of problems. As easy a concept as it is, recognizing that the complement needs to be used will become a skill later on. Okay. And once again, I'm reviewing intersections and unions. Remember, if they're independent, A times B will give you the product, it will give you the probability of them both happening at the same time, which is called the intersection, which is this symbol. When you're adding things, one or the other happening, you have to add the probability of A plus the probability of B minus the intersection. You don't want to double count things, okay? And again, this intersection could be 0 if the events are mutually exclusive, okay? It could be their product, which is A times B, if the events are independent, IND, independent, or it could be a given number if it's neither independent nor mutually exclusive, okay? And then conditional probability, which we'll get to later on, okay, is going to be, by the way, this reads probability of B given that A happened. So a lot of times people look at it as this: B given A is the denominator, okay? And we will get into this later on. So the three big things we're learning in this chapter, the three big ones, okay? And I go over these words a lot, are conditional probability, okay? Independence, and mutually exclusive. Where is the mutually exclusive word? I guess I have it here. Let's see here. Guess I got it right here. Those are the big three. Those are the big three things we're working on. Okay? All right. So again, we are just right now just practicing. We're just getting our minds loose. We're practicing all kinds of probability just to get your mindset ready to go. Because the AP test sometimes has real simple probability, and if we haven't done it, it'll be challenging. Now, I'm not going to do every single problem in this video. Some of these, just take forever to explain, and they're not necessary to do at times, okay? And I'll point that out as we're moving along here. Again, stop the video whenever you feel you need to, okay? All right, so we're on 2A. So let me circle that so you see where I'm at. We're on 2A. All right. A bag containing 5 red, 7 blue, and 8 yellow marbles. Find the probability of drawing a blue marble, then a blue marble with replacement. In other words, you put it back in there. Okay, no problem. Let's see here. How many marbles are in here? 20. Okay, so this ends up being 7/20ths times 7/20ths because you put it back. No problem. And you can see the math there for that answer. Okay. The next one, a blue marble, then a red marble. A blue marble, then a red marble. Okay. So a blue marble would be 7/20ths. And then without replacement, then a red marble, red would be 5/19. You can see the math on that. Okay. Triple I here. A yellow marble, then a red marble with replacement. A yellow marble is going to be 8/20ths. And a red marble, it's going to be 5/20ths because you put it back. And then there's your answer. Okay. And then a blue, then a red without replacement. So you're not going to put it back. So a blue one is going to be 7/20ths times, and then another event. Then a red marble, which will be 5/19ths. Then another red, and you've already got a red the first time, so it's 4/18ths. And there's your math on that. Okay. All right. Let's go to B. Okay, 2B right here. Okay. Based on the table provided, find the probability of selecting a girl. All right, a girl is going to be 41/80ths. You see that pretty clearly there, okay? By the way, in these tables, which we'll get to later on in the course, okay? This table is a, let's see, row times column. This is a 2x3 table, okay? These numbers are called marginal totals because they are totals in the margin. And this is a course called a table total, okay? And it's not part of the table technically, it's a 2x3 there. Okay, you don't have to know all that, but just pre-teaching stuff that will come up later. All right, a sophomore. What are the chances of being a sophomore? That's going to be 25/80, no problem. Okay, how about a junior boy? A junior, 11, that's a boy. That's going to be 15/80ths, okay? All right, no problem. And then how about a non-freshman girl? A girl that's not a freshman, okay? So a non-freshman girl. So let's see here. Where are the girls? And so you're going to add these two up right here and divide it by 80. Okay, a non-freshman girl. No problem. Again, simple probability. Does that show up once in a while on the AP test? It does. It's like question A of A through D, but they show up. Okay. All right, let's go down to C. We'll do C and D. I'll be able to get E and F at the same time. Yeah, that'd be good. Okay. All right. So let's do C and D here. All right. 60% of voters approved Proposition A and 90% approved Proposition B. Pretty common in California to have all these propositions. Find the probability of voter who voted for both A and B. Now, I didn't write this. Let's assume that the votes are independent so we can multiply, okay? And it's all kind of written out for you here, so it's pretty easy. For both A and B, that would be 0.6 times 0.9, assuming they're independent. Voted for A, but against B. This is where you're going to use the complement. Okay, you can see right here that voting for A is 0.6. Voting against B would be 1 minus 0.9. Okay, 1 minus 0.9. That's the complement. Okay, and voting against them both, you would take the complement of both. Okay, and then multiply it. Okay, again, not super duper hard, but again, it's so good to go over these real simple ones before we get into the ones that are very specific for what we're doing in this chapter. All right, a deck of 52 cards. Probability of getting a king and then an ace. If you don't know, there are 4 kings, okay, and there's 4 aces too. Without replacement, if you get a king first and then you have 1 less card, a little better chance to get an ace. So it's going to be 452 times 451, and there's your probability, which is not real high. Okay. 1 red card and 1 black card without replacement. So a red card is actually half. That's actually half. If you wanted to put half, that's fine. Okay. And then a black card, if you got a red card first, there's still 26 left, but 51 is, there's 1 less card to get. Okay. This is, by the way, called conditional probability because the denominator is changing because you have a situation where the numbers are changing, okay, because of the conditions of the game are changing, which is how you get into counting cards eventually. Okay, a queen and a spade with replacement. All right, fine. So a queen, there's 4 of those, and a spade, there's 13 of those. And because you put the queen back into the hand, then you still have 52 as your denominator on the second one. Okay. All right. How about E? A 6-sided die is rolled 3 times. All right. All 3 are 5s. Remember, a dice, they are all independent because the dice has no memory and there's always replacement because the dice it's the same die you're rolling every time. So all 3, obviously all 3 5s, we have a 5 is a 1/6 chance, so 1 out of 216. All 3 are odds. Again, odds are 1, 3, 5. Pretty simple. 1/8. No 5s. No 5s. Here we go again. You got to use the complement. There are no 5s would mean that you got I found this problem kind of interesting that it's just over 50%. If you roll a die 3 times, you might get a 5 because you have to get a non-5 3 times in a row, which is 5, 6 to the 3rd power. Okay. Now, I'm going to circle this one. This one, you got to know at least 1. They love these problems on AP. At least 1. At least 1 is 1 minus none of them. So at least 1 odd. So I'm going to go 1 minus the chances of getting all even numbers, which is to the 3rd here. Okay. So that's 1 minus 1/8, which is 7/8. You got a real good chance to get at least 1 odd, a 7/8 chance when you roll 3 times. Okay. That's a common problem, the at least 1 problem. And you're going to see that quite a bit here. Okay. All right, for 2F, we got two dice. One is 1 through 6, and the other is A through F are rolled together. So there's a little bit different. A number larger than 4. Well, a number larger than 4 is only the 5 and the 6, and we're only talking on one die here. So that's 2 of the 6, which is 1/3, 0.33. Okay, a consonant letter. I barely know what a consonant is, but let's go. We got A, B, C, D, E, and F. Okay, the consonants are B and C and D and F. So 4 of the 6, which is 2/3. All right. Now the next one, an even and a vowel, and is multiplied if the events are independent. Let me say it again. And is multiplied if the events are independent. Well, these are clearly independent because one die doesn't affect the other one. So an even, which is 2, 4, or 6, is a half chance. And then a vowel is only if 2 of the 6, I have them listed here, A and E, 2 of the 6, and then there's your answer right there. Okay. Now the next one is an even or a vowel. Ooh, this problem is awesome. I really, really like this problem, and I'm going to sit here for a little while on this. Okay. So settle in here. We're going to sit down and we're going to really look at this problem, an even or a vowel. Now you can see the answer down here is 2436. What's going on with that? So let's look at this. And again, settle in here. An even or a vowel. Okay, the first thing we're going to do, let's figure out how many different combinations we have. And remember, or means addition. Or means addition. So the simple thing to do is to look at all the particular combinations here. So, and the probability of getting an even number on a roll of 2 dice would be 18 out of 36. If you think about it, and we're going to do the math on this. If you think about it, let me get rid of that. If you think about it, there are 36 rolls of these 2 dice, 6 times 6. That's the counting principle. Half of those are going to be even, okay? Now, a vowel, you're going to have 12 of those be even. I'm going to show you in a minute on this with sample space. But the answer is not 30 out of 36. We double counted some stuff. So we're going to subtract out the intersection. Okay, so remember our formula. Probability of A plus the probability of B minus probability of A intersection B. A intersection B. Okay, let's check it out. We're going to go the long way and do sample space. Like I said, settle in here. Okay, so there are 36 different rolls. You could get I'm going to list them all. I'm going to start way over here to the left. 1A, 1B, 1C, 1D, 1E, 1F. Okay, here we go. 2A, 2B, 2C, 2D, 2E, 2F. 3A, 3B, 3C, 3D, 3E, 3F. Oh boy. 4A, 4B, 4C, 4D, 4E, and 4F. 5A, 5B, 5C, 5D, 5E, and 5F. 6A, 6B, 6C, 6D, 6E, and 6F. Wow. Now, I told you in previous lessons that if you're not sure how to do the problem, go to sample space. And if it's less than 50, you'll be fine. All right, so the question is, An even or a vowel, an even or a vowel. All right, so the even numbers, even, all of these are even, right? Twos, even, twos, even, twos. I mean, twos, fours, and sixes. Got it. Now, so I'm going to write over here now. So 18 of the 36 rolls are even. Okay. Now, how about the vowels? How about the vowels? Okay. The vowels are A. Look at all these vowels are A. And the vowels are E. A and E. Aha. So 12 of those, right? But you can tell that we have double counted and we have an intersection. What's great about this prompt is you can physically see the intersection. Here's an intersection right here. 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 Right here and right here. There are 6 of them. Okay, so we got to subtract that out. So again, probability of A plus probability of B minus probability of A intersection B. There it is. I have it in writing. Okay, that's pretty cool. So basically, I use sample space to figure this problem out. Okay, which is kind of cool. All right, so let's do it a different way. Okay, let's do it a different way. Let me clear this. Let's do it a different way. Okay, an even or a vowel. Okay, I know that rolling the dice is independent. I know that. Okay, so the chances of me getting an even number was 18 out of 36, which I'm going to write as 1/2. The chances of me getting a vowel was 12 out of 36, which is 1/3, right? And I'm going to subtract the intersection. And the intersection will be their product because the events are independent. Notice from your notes, this is 1/6 or 6/36. Okay, this is 18/36. And this is 12/36. There it is. So you didn't necessarily have to use sample space to get that problem. You could have gone the probability of A, which is 1/2, plus the probability of B, which is 12/36 or 1/3, minus their intersection. And in this case, the intersection is their product right here because these two dice are independent. That is a cool problem. I hope that that long explanation makes sense to you. Okay? All right, let's keep rolling. This is a very long day. I won't do all the problems. Sometimes I'll just stop and let you guys kind of play with them. They're not all worth putting 10 minutes on a video on because they're too complex, but they're pretty cool. Okay. All right, here we go. Probability event on question 3. Event A is 73%. What is the probability of event A occurring 4 consecutive times? This is easy. 4 consecutive times would be 0.73 to the 4th. Okay. All right. And then next one, A occurring 2 times, then not occurring. Well, not occurring is the complement. And I'm using exponents to signify how many trials we got. Okay. All right. Now, wow, this is a really cool problem right here. A really cool problem. And again, I'm going to sit here for a little bit. Okay. This one's got stars on it because it's way too hard for this particular chapter. This will actually show up in chapter 6 a little more commonly. And these are binomial. Okay. If you remember what binomial is in general, It's when there's only two outcomes and the outcome never changes, okay? And so we're doing a lot of binomial stuff right now, but we're not really focused on the entire binomial distribution. So I'm going to sit here right now, and again, this would not be something I would test you on in this particular chapter. But let's play with this, especially those kids. I'm always concerned about maximizing each kid's potential as best I can. So I got some cool problems in here for them too. And again, I won't do all of these, but I'm going to do this one, okay? Event A occurring no more than 2 times in 6 trials. So in other words, it occurs 0 times, 1 time, or 2 times. 0 times, 1 time, or 2 times. And you can kind of see my sample answer here, okay? This is occurring 0 times, this is occurring 1 time, and this is occurring 2 times, 0, 1, and 2. Now, this involves combinations, okay? But it also could involve, if you wanted to shortcut it, Pascal's triangle, okay? So combinations, remember, if you have 6 trials, there are 7 things that can happen. It could occur none, no times, once, twice, 3, 4, 5, or 6. There's actually 7 things that can happen. So real quick, I'm going to flip over to I'm going to find row 6 of Pascal's triangle. I have it already here. Okay, row 6 of Pascal's triangle. All right, so row 6 of Pascal's triangle is right here, okay? Notice it's got 7 different terms, 1, 6, 15, 20, 15, 6, 1. The 1 means you can start at either end, but the 1 means there is one way for that event to occur all 6 times. It occurs all 6 times, okay? The 6 means there are 6 ways for that event to occur 5 times, meaning it would not occur on the first trial or the second trial or the third or the fourth or the fifth or the sixth. I'm going to go in more detail in a different chapter on how sample space is related to Pascal's triangle. I've actually done it in a previous lesson, so I'm not going to spend too much time on that. But now, I remember the numbers, 1, 6, 15, 20, 15, 6, 1. Okay, got it. All right, so I'm going to go ahead and go back to this. Okay, I'm going to write these down, okay? We got, we have 1, 6, 15, 20, 15, 6, and 1, okay? Now, I want these 3 right here, okay? This is the probability of it occurring 6 times, 5 times, 4 times, 3 times, 2 times, 1 time, and no times, okay? All right, so I'm going to focus on the 15, the 6, and the 1, okay? I'm going to clear this and write it down here. So we got 15, 6, and 1. Okay, and I'm going to do some multiplying here. I'm going to set my parentheses up, and I'm going to be adding these. And again, this is not a problem that you would be asked to do on this chapter, but it's really cool to get your mind going on this. Okay, so there's actually 15 ways for this situation to occur twice in 6 trials. For example, it could happen on the first trial and the second trial, the first trial and the third trial, the first trial and the fourth trial, the first trial and the fifth trial, the first trial and the sixth trial. If I go through all those sequences, there's 15 of them, okay? So that's going to be 0.73 squared, and you notice that right here. And notice this is 6 choose 2, okay? Times 0.27 to the 4th. Notice that the 2 and the 4, the exponents, add up to 6 because there are 2 successes and there's 4 failures, okay? The next one will be there are 6 ways for this event to occur once. So I'm going to put 0.73 to the 1st and 0.27 to the 5th, because if it occurs once, it doesn't occur 5 times. And the last one is occurring no times. That means 0.73 never happened. And by the way, 0.73 to the 0 is 1, and 0.27 to the 6th. Okay? All right, so that problem, again, very tough problem. I did a star on that. Sometimes I have triple stars on some of these. That's a cool problem. That would be something that we would do in chapter 6, and it would probably be on the calculator. It's actually very easy on the calculator, but that's for another chapter. Okay. Hope you enjoyed that problem. It's kind of cool. All right, B. Going to go over to 3B now. Probability of an event is 85%. What is the chances of A occurring 6 consecutive times? No problem. If they're independent, which I'm assuming they are here, 0.85 to the 6th. All right, event A occurring for the first time on the 3rd trial. When an event occurs for the first time, that is called the geometric distribution. By the way, geometric distribution. That is chapter 6, by the way, next chapter. But I'm just showing it to you here. First time on the 5th trial. That means twice in a row you didn't get it. So 0.15 happened twice, and then it did happen. Okay? Now, at least once. Let's sit on this problem for a little bit. This one you got to know. At least, no, I shouldn't say that. That's not true. Sorry about that. At least twice. So I'm going to skip this one. We will hold you accountable for at least once problems right now, but not at least twice. That'll be later. But if you want to play with that, you can. At least twice is 1 minus none or 1, which I have here. None minus none or 1. So you high-end students, if you want to play with that, feel free, but don't worry about being held accountable for that. Okay, that's just kind of a bonus problem. I got a bunch of bonus problems in here, because I found when I do these, some kids fly through and they want something more challenging, so I provided them. All right, C and D. A die is rolled 4 times, one after another. Here we go, a die, and we know a die is independent. We know that. What are the chances? These are all odds. All odds would be 1/2 to the 4th power, no problem, okay? There is at least 1, 2. All right, you have got to know at least 1 problems. Once again, at least 1 is 1 minus none of them happening. 1 minus none of them. So a 2 is a 1/6 chance. So not a 2 would be 5/6. I'm going to do that 4 times. It's number 4. I'm going to go 1 minus that, and that gives me my answer of at least 1. Okay. And then not all are 3s. Not all are 3s. Okay. And you can see the math on this one. That's not super hard. This is the one above it that you would be accountable for in this chapter. Okay. And I have a bunch of these to practice with you. Okay. 3D. A slot machine has 3 independent wheels, each having 3 or 8 equally likely outcomes. No problem. What are the chances that all 3 wheels show apples? They're all independent. So you can see that there are 3 apples. So 3 of the 8 are apples, and all 3 of them would be about 5%. There are no fruit showing. Not really sure what a fruit is in this case. I guess that's the apples and the cherry. So that would be at 2/4 or 1/2 to the, let's see here. That would be 1/2 to the, it's actually 1/2 to the 3rd. I had the wrong, yeah, wondering what I did there. This is 1/2 to the 3rd power. Okay. It's 3 independent wheels, not 4. 1/8. Sorry about that. Glad I caught that. All right. And there's at least 1 star. Here we go again. At least 1 star. At least one. You got to know this. At least 1 is 1 minus none of them. Okay, so the chances of getting a star is 2 of the 8, okay, which is reduced to 1/4. So not a star would be 3/4. We're going to take that to the 3rd power and go 1 minus. And that's how you do the at least 1 problems. Those are very common on the AP test, the at least one problems, okay? So we keep working on those. Okay, down to E and F, and I got page after page of this, okay? All right, so here's, let's see, I'm gonna just a little smaller. Okay, a toy company produces 4 types of toys and randomly puts them into grab bags. They produced 26% type A, 18% B, 30% C, and the rest type D, okay, which is 26%. What is the probability you pull out one toy of B or C? Now, remember the formula for OR problems, okay? Remember the formula for OR problems. It is probability, in this case, of B plus probability of C minus the intersection of B and C. Now, in this case, this intersection is 0 because you can't type out a toy that's BC. It's one or the other. You can't have that overlap. So these toys are mutually exclusive. You can't pull out a toy that's both B and C. So that's why it's just 0.18 plus 0.3. Technically, this answer is 0.18 plus 0.3 minus 0 because there is no intersection. Okay? All right. Not type A, the next problem, not type A, is 1 minus the 26%. No problem. Okay? Now, the next one, 2 toys that are both type C, and we're going to assume that we replace the toy or something. I'm just going to go with replacement. Don't worry about the replacement, non-replacement. Assume this is replacement. So that'll be 0.3 squared. Okay? And then item 4, 2 toys, neither of which are type C. Well, if type C is 30%, not C would be 1 minus 0.3 or 70%. Hence, you get 0.7 squared. Okay? Now, here we go again. At least one. I'm hammering on these. At least one type D in 5 trials. At least one type D in 5 trials. Okay, type D is 26%. So what I'm going to do is go 1 minus that and get 0.74. Take it to the 5th power and then go 1 minus. And that will leave me with at least one. Okay, 1 minus none of them is the answer to that question. Done it a lot. Now, the next one, not all toys of type B in 4 trials. Not all of type B. All right, well, not all of them are B. That would be this pretty simple problem. Take type B to the 4th power and go 1 minus that. Okay. Next one there. Okay. A candy company produces, I'm on 3F, by the way, 3F. A candy company produces 5 flavors of candy and randomly puts them into their candy bags. They produce that percentage. Okay, you can, the rest are E. E is 32%, by the way. What is the probability that you, by the way, I did this because all of these need to add to 100%, which is something we talked about at the beginning of the course. Sorry, I didn't point that out in 3E. Okay, pull one candy flavored A or D. Again, this is 0.12 plus 0.15 minus 0 technically, because you have to subtract out the intersection of candy that would be AD flavored, which doesn't exist, okay? Neither B nor C, so you're going to go 1 minus this. I think I would do it this way. It would make more sense to me. I would add together B and C and go 1 minus. I like that. That's a little cleaner looking to me, okay? Okay, I am now on 3 right here, okay? Pull out 2 candies, both being either B or C. I mean, B or E. Well, B or E, 32 and B is 18, that adds up to 50%, okay? Two of them. So really what you're doing is you're doing this, 0.18 plus 0.32 squared. You're doing it twice, okay? And again, assuming there's replacement here. We don't have the totals to count down, assuming we have replacement, okay? Or assuming we have giant amounts of candy where pulling one out does not significantly change their proportion. That is a concept we'll talk about in subsequent chapters. It's pretty cool. Okay. And then 4, pulling out 2 candies, neither of which are A or B. Neither of which are A or B. All right. So A and B together make 30%. So not A would be 1 minus 0.12 plus 0.18. I know I'm going the long way here. So that ends up being 0.7, and then you're going to square it. And again, we're assuming that we have so much candy that pulling one out does not significantly change the percentage. So we're just going to keep the same percentage and not worry about doing a non-replacement situation. All right, here's an at least one problem. At least one. All right. At least one is 1 minus none. I've said it a million times. At least one candy flavored B or C. So let's get B and C. B and C right here, those add up to 18, 20, 41%, all right? So not would be, not BC is 59. And remember, at least one is 1 minus none, which is the complement. Okay? And the last one is a similar one. Pull out in 7 trials and not all candies of flavor A or E. Not all candies of flavor A or E. Okay? So A and E, 32 and that make 44%. And you can see not all of them. That's a different problem than at least one. By the way, these are different if you haven't noticed that. Okay, one uses the complement here and one does not. Okay, they're worded differently. This is the one that I see a lot on the AP test. I say a lot, probably in 30 years of this or whatever, probably around 30 times, once a year. Okay. Okay. Now we got a few problems to go here. I'm not going to do all of them, but this is just a great way to get a lot of practice in quickly. Okay, there we go. Jake is a 65% free throw shooter. Now we're going to make a fairly big assumption here. Assume every free throw shot is independent. That can be debatable because sometimes kids gain or lose confidence when they make or miss a free throw at the beginning of a 2-shot foul or a 3-shot foul or whatever. But the NBA actually studied this, and they pretty much came to the conclusion that every free throw is independent for most people. Okay, all right. What are the chances he misses his first 5 shots? That's 5 in a row. There's only one way to do that, and that's to do the complement of 0.65, which is 0.35, and then go to the 5th power. All right. 2, he makes his first shot on the 4th attempt. All right. We've seen this before. I'm going to say it again. This is the geometric distribution. Okay, geometric distribution. And this is chapter 6. So we're not there yet, but we can still do the problems. Makes his first shot on the 4th attempt. What that means is he missed 3 times in a row. So the 0.35 to the 3rd happened. And then he finally makes one. So it's only about a 3% chance that you wouldn't see a success until the 4th shot. So if you're a coach and that happened, you might ask what's wrong. It's so rare. Okay. Aha, here we go again. At least one in his first 6 attempts. At least one. 1 minus none. 1 minus none. There it is right there. I'm not going to go through this. I've done it so many times. And then making 10 consecutive shots is would be, there's only one way to do that. 0.65 has to happen 10 straight times, about 1% chance. Okay. And if that happened, you might wonder, are you still a 65% free throw shooter? You might be better because 1% is so rare that you would think this probably isn't chance, you've improved. That concept is called inference, making a judgment based on what happened. And that shows up in chapter 7 through 12. Okay. All right. Let's go to H. The probability of catching a spy in your company. I love these spy questions. You know, there's always spies in an organization. They're important to the boss. You know how it is. It says your spy in your company is 15%. Probability of a spy surrendering, cooperating, secret information is 35%. All right, so you got two different situations, catching them and having them actually give up information. What is probability of catching a spy, but he refuses to cooperate? Aha. So you caught the spy, 15%, but they didn't cooperate, so I did the complement of that. By the way, I'm going to preview something. Eventually, you can do these kind of problems on tree diagrams, okay? So a tree diagram would be something like this, 15%, okay? And then this would be 85%. So this is catching the spy and not catching the spy. If you catch the spy, two things can happen. They can give up information, or they can not give up information, okay? Or they can, same thing here, you can, if you don't catch them, of course, if you don't catch them, they won't give up any information. You don't catch them, but there's your tree diagram on that one. And we are on this branch. Eventually, we'll do stuff like that. Eventually, tree diagrams. Tree diagrams are the same thing as the Punnett square. If you may have done that in biology, and this is coming up soon, okay, where you have 15% and 85, and then you got 35% here and 65% there, and you fill in the 4 quadrants there. That is something you might have done in biology. Okay, we do tree diagrams in statistics. You don't necessarily need them, but they're kind of nice. Okay, so in this case, we're not going to do that. We're just going to kind of fly through them here. All right. Item 2 here, not getting information. Okay, there are actually 2 ways to not get information. There's 2 ways. This is a cool problem. Okay, again, it's a fancy problem. There's an 85% you won't get any information because you don't catch them. But there's also another way to not get information. That's right here. That is if you catch them, but they don't say anything. So it's actually about almost 95% chance of not getting any info. That's a cool problem. This kind of problem can show up in, I've seen a problem very similar to this in an FRQ. So you might want to take a good look at that one. I've seen that one. There is a possibility you would get something like that. Okay. All right. Getting some information from one suspect. All right. So getting some information would be this. Okay. That's basically the complement of that problem. There's only one way to get information. You have to catch them, 15%, and then they got to talk, 35%. Okay. All right. Now, the last one, getting some information from 4 suspects. Okay. Getting some information from 4 suspects. This is a fancy way of this right here. This is a fancy wording on this one. Some information from 4 suspects. That's at least one person talking. Fancy way of looking at that. Pretty cool. So I'm going to go with 1 minus none, right? And I did this problem already. There's a chance of getting no information. So this is my problem, 1 minus none. That's another one of those at least one problems worded differently. Okay. Now I'll say it for the millionth time. These are some of these problems are very difficult. Okay. And we are just whetting your appetite, trying to do 4 or 5 days of some probability problems just to get you ready for the stuff that I'm in charge of specifically teaching you. okay? But I think without some of this, your mind isn't polished and ready to do the harder ones, to do the ones, I should say harder, to do the ones that are required of you, okay? All right, last ones here. And I'm gonna cut some of these off because there's so many of these. So 3I, and again, I'm not gonna do every single one of these, okay? 3 students are asked to randomly pick a number between 1 and 10. Find the probability that all 3 numbers are odd. No problem. All 3 numbers are odd. Easy, right there. Okay. Item 2 and 3, I am not going to do. So if you want to look at those and try to play with them, that's great. If you don't want to play with them, that's okay too. I think I went over the top on those. Okay. I went a little crazy on that. All right. But if you want to pause the video and check it out, great. You're not accountable for them. I put these crazy stars by them because I went a little wild on them. Okay. All right. And then J, I will do the first one in J and then we're going to stop. Okay. So 3J, you can correctly answer 75% of the questions asked in your math class. If there are 10 questions in the final, find that you probably get all of them correct. Well, all of them correct. I didn't really have to write the 0.25 to the 0 there because I had to get 10 straight correct. 0.75 to the 10th. Okay. And this one is starred. Okay, this one is starred. I'll do this one here. It would be something you would need to know in chapter 6. It's a binomial problem. Okay, exactly 7 correct. Exactly 7. Notice that the 0.75 happened 7 times and the 0.25 happened 3 times. Okay, 10 to 7 is Pascal's triangle. There are 10 questions and you got 7 correct. This is something we would do in the binomial distribution on the calculator later in chapter 6, okay? So I'm gonna stop there on that particular problem. So if you want to pause the video and check this one out, at least 8 correct means getting 8 or 9 or 10. You can check that one out. Don't worry about being held accountable for that, but it's kind of good to check it out. That's a preview of chapter 6. Preview of chapter 6, like I keep saying, okay? All right. The last 2, I probably got a little wild on these, as I am prone to do. So I'm just going to go ahead and leave these up for a second. If you want to play with those, feel free to play with them. You're definitely not going to be held accountable for those. In fact, the last one I have like triple starred. It's a crazy, crazy problem. These probably don't belong in the notes, or a little extensive, but again, I like to mess around. And if some kids get into this and they want more and more and more, so this is kind of my way of checking it out. So if you want to pause there and check it out, that's great. Okay, so that is day 4 of chapter 12. And again, around day 6 is when I start getting real specific on problems that would happen on the AP test, okay? These other problems have a chance of happening, but not as great a chance. But if we don't play and sit and do some probability, I think it hurts you long term to not have that practice, okay? Hope you enjoyed it. See you later, Stat Nation. Take care.